I want you to picture something with me just for a second. Imagine you are walking down the floor of a modern, massive industrial factory.
Oh, those places are just incredible to see in person.
Right. I mean, it is immaculate. You're surrounded by these gleaming, brushed aluminum machines.
Yeah.
You've got robotics arms moving with, pinpoint precision.
Everything perfectly timed.
Exactly. Everything is highly organized, perfectly engineered. It is humming along, basically the absolute picture of efficiency.
Yeah.
But if you stop walking for a second, just close your eyes and really tune your ears beneath the heavy clanking of the metal and the low bass of the motors.
You'll hear it.
Yeah, there's a persistent, quiet sound. It's a hiss.
It blends in so perfectly, though. It's like a steady, localized breeze that just never takes a breath.
Right, a continuous hiss. And you stand there and you watch the floor manager walk right past it. And you watch the maintenance team, they drive by on a cart.
Just completely ignoring it.
Yeah. A forklift operator parks right near it.
Yeah.
And nobody even turns their head.
Because it has been completely grandfathered into the environment. I mean, it is no longer an anomaly. It's just part of the room's acoustic signature.
It's just part of the factory soundscape.
Yeah.
But today, we are going to completely reframe how you hear that little factory hiss.
We really are.
Our mission today for this deep dive is to take that sound, which feels like, completely harmless background noise, and expose it for what it actually is.
Which is an invisible, profit-draining hemorrhage.
Yes, exactly. We are going deep into the world of industrial compressed air. We're going to look at the staggering physics of why this stuff is so incredibly expensive, the psychology of why we just ignore it, and, well, a specific, highly profitable behavioral strategy to fight it.
The Audible Loss Method.
Right. And whether you manage a multi-million-dollar manufacturing plant or you are just fascinated by how massive inefficiencies manage to hide in plain sight in almost any organization, you are going to walk away from this conversation seeing and hearing the world a little differently.
Absolutely. It changes your perspective.
Okay, so let's unpack this. We have a stack of technical manuals today from Natural Resources Canada, the U.S. Department of Energy, some ISO standards, and various O&M guides. But before we can even talk about why that little hiss is so detrimental, we need to establish what compressed air actually is.
Because it's definitely not what most people think.
Right, because frankly, before looking into the source material, I assumed it was just air. And, air is free, right?
Yeah, that underlying assumption that air is free is the psychological trap that costs global industries billions of dollars every single year.
Billions. Yeah.
Oh, easily. I mean, ambient air just sitting in the room around us is certainly free, but compressed air is an entirely different beast. In the manufacturing world, compressed air is actually referred to as the fourth utility.
The fourth utility. So like alongside water and power.
Exactly. You have water, you have electricity, you have natural gas, and you have compressed air. But there is a massive distinction here.
Which is what?
Well, water, electricity, and gas are generated by outside providers, right? At a highly regulated, massively efficient scale, and then they're piped directly into your building.
Right. You just pay a bill for what you use.
But you have to generate your fourth utility yourself right there on the factory floor using your own equipment.
And the process of generating it is, well, it's mind-bogglingly inefficient. I was diving into the physics of this, looking at the energy audits in the DOE manuals, and my jaw dropped.
It's hard to believe until you see the math.
We're talking about a process that basically defies all modern expectations of industrial efficiency.
The physics are just utterly brutal. I mean, to understand the financial cost of that tiny hiss, you first have to understand the sheer violent force required to create the air that's driving it.
Right. Let's break that down.
Okay, so let's say you want compressed air at a standard industrial pressure. It's usually around 100 pounds per square inch, or seg.
Okay, 100 psi.
To achieve that, an industrial air compressor has to take roughly 7 volumes of atmospheric air and violently crush it down into one single volume.
A 7-to-1 ratio. I mean, you are literally fighting the natural state of the atmosphere.
You are fundamentally fighting molecular dynamics. And when you force gas molecules that tightly together and that rapidly, the laws of thermodynamics extract a massive toll.
A toll in the form of heat. Right.
Exactly. You might remember the ideal gas law from, high school chemistry. When pressure and volume change, temperature changes.
TV equals nRT, something like that.
That's the one. The electrical energy you are pouring into that compressor motor doesn't just neatly store itself as potential energy in the air. The vast majority of it is instantly converted into heat.
Because the molecules are just slamming into each other.
Right, they're bouncing off each other in an increasingly confined space, which generates immense thermal energy. So if we look at the raw numbers, the efficiency gap is staggering.
Okay, I want to hear the exact math on this.
Yeah.
Let's trace the journey of, say, a watt of electricity.
Sure. Imagine you have a massive electric motor driving your rotary screw air compressor, and you feed 100 horsepower of electrical energy into that system.
Okay, 100 horsepower going in.
Out of that initial 100 horsepower, roughly 80 horsepower is instantly lost as the heat of compression.
80%. Just instantly radiated away as pure heat. That is wild.
Gone. So now you are down to 20 horsepower of potential energy actually stored in the compressed air. But, and this is the kicker, you can't even use that air yet.
Why not?
Because you squeezed 7 volumes of atmospheric air into one, which means you also squeezed all the ambient humidity into a tiny space.
Oh, right, the water vapor in the air.
Exactly. The air is now supersaturated with water vapor, and it's incredibly hot. If you send that directly into a factory's steel pipes, it will basically turn into a rainstorm inside the plumbing.
It would just rust the whole system from the inside out.
It would destroy it. So you have to run this hot, wet air through an industrial air dryer and a series of filters, and pushing the air through that dryer and those tightly woven filter meshes creates friction and pressure drops.
So we lose even more energy.
Right. That eats up roughly another 9 horsepower.
Okay, so we started with 100, lost 80 to heat, lost 9 to drying and filtering. We're down to 11 horsepower.
And we're still not at the tool. Next, the air has to travel through hundreds of feet of piping. It has to navigate elbows, valves, drops to reach the actual factory floor.
And pipes have friction.
Fluid dynamics tells us that air scraping against the inside of a pipe creates friction, which means more pressure drop. That's another 2 horsepower loss.
Leaving us with 9.
Finally, you reach the pneumatic tool itself. Say it's an air-powered wrench or a drill. Converting pressurized gas back into mechanical rotary motion inside that tool is not a perfectly efficient process either.
Right, the tool has moving parts.
Exactly. The pneumatic motor inside the tool loses about 2 more horsepower to mechanical friction and exhaust.
So let me get this straight. Out of my initial 100 horsepower of highly expensive electrical input, I am left with about 7 to 9 horsepower of actual useful mechanical work at the tool.
That is the grim reality of pneumatic power. You are operating at less than a 10% efficiency rate from the electrical meter to the mechanical output.
I mean, I was trying to visualize this when I first saw the numbers in the DOE report. It's like, imagine you throw a party and you order a massive 100-slice pizza.
Okay, a big pizza.
The delivery driver shows up, hands you the box, and you immediately take 91 slices, walk over to the trash can, and just dump them in.
It sounds absurd when you put it like that.
Right. You're left with 9 slices to feed everybody. With margins that catastrophically bad, shouldn't we be treating every single slice of that pizza like absolute gold?
You would think so.
Why on earth is anyone using compressed air if it's this inefficient?
Well, the environment of a heavy industrial floor dictates the necessity. It's easy to ask, why not just plug in an electric drill?
Yeah, because modern electric motors are incredibly efficient, right? Often hitting 90% or more.
They are. But in many heavy industrial settings, electrical tools are either wildly impractical or extremely dangerous.
I assume you mean explosive environments, like chemicals and stuff.
Exactly. Think petroleum refineries, chemical processing plants, or even agricultural grain elevators.
Wait, grain elevators, why are they explosive?
Grain dust is highly combustible. If you use a heavy-duty electric tool in those environments, the internal brushes of the motor can create a microscopic spark.
Oh, wow.
And in a saturated atmosphere, that single little spark can level a city block. Pneumatic tools don't spark, they don't have electrical short circuits, they run entirely on the kinetic energy of expanding gas.
So it's an absolute safety mandate in some places. You literally can't use electric.
Correct.
But what about, say, a regular car manufacturing plant? They aren't explosive. Why use air there?
2 main reasons: torque-to-weight ratio and durability.
Okay, torque-to-weight ratio. How does that work?
An air-powered impact wrench can deliver massive amounts of torque instantaneously. And because it doesn't contain heavy copper coils or complex electrical stators, it is incredibly light.
So it's more ergonomic for a line worker to hold for like 8 hours a day?
Exactly. Imagine holding a heavy electric drill over your head all day versus a light pneumatic one. Furthermore, if you stall an electric motor, if you push it too hard and it stops spinning while the power is on, it will overheat and burn out its coils.
Yeah, I've burned out a drill doing exactly that.
Right. But if you stall a pneumatic tool, the air just stops flowing. No harm done. You can drop them, cover them in grease, and beat them up in ways that would destroy a standard electric tool in a matter of days.
Okay, so industry absolutely needs compressed air. It is a luxury utility, but a vital one.
A very necessary luxury.
But the financial structure of owning an air compressor, it seems totally counterintuitive. I was looking at the life cycle cost analysis and the source materials for these massive machines, and it completely upends how we normally think about buying equipment.
It really does. People tend to obsess over the initial capital expenditure, right? The sticker price on the machine itself.
Which makes sense for most things you buy.
Sure. But if you look at a standard 10-year lifespan of a heavy-duty industrial air compressor, the initial equipment purchase only accounts for about 12% of the total life cycle cost.
12%, that's nothing.
Routine maintenance, parts, and oil changes account for another 12%.
Which leaves 76% of the cost over a decade.
76% of the total cost of owning that machine is the raw electricity required to run its motor.
So if you're the factory manager, buying the actual machine is essentially just a down payment on a decade-long astronomical electricity bill.
Exactly. The compressor is really just a mechanism for consuming electricity. And this circles us right back to that hiss on the factory floor.
Right, the invisible leak.
If 76% of your equipment cost is electricity, and physics dictates that 91% of that energy is lost as heat and friction before it does any work.
The absolute last thing a rational business can afford to do is let the 9% of air they successfully managed to produce just leak out of a broken pipe.
Precisely. It is financial madness.
Which is exactly what they do. I mean, this is the part of the data that honestly made me want to pull my hair out. Industrial energy audits consistently show that in a typical unmaintained manufacturing plant, 20 to 30% of the total compressor output is lost purely to leaks.
It's a staggering figure.
Let's just sit with that math for a second. They lose 91% of thermodynamics, and then they take the precious 9% that's left and just leak a third of it directly into the room.
Right back into the atmosphere.
So here is my central question. If this is so incredibly expensive, why on earth do smart, profit-driven factories just allow this to happen?
The answer lies in human psychology, specifically the phenomenon of normalization and how it applies to factory culture.
Normalization.
Think about how we react to the failure of other utilities. If you have a 2-inch water main burst in the middle of a factory, what happens?
Oh, it's pure chaos. You get a massive puddle, someone slips, production halts immediately, and you have people running around with mops and wrenches. It absolutely demands a reaction.
Right. It creates a visual and physical crisis. If a hydraulic oil line ruptures, it's an environmental hazard, it's a slip hazard, and it ruins whatever product it touches.
So the leak leaves an undeniable physical footprint that forces human intervention.
Exactly. But compressed air is uniquely invisible. It doesn't leave a puddle. It doesn't stain the concrete. It doesn't smell like gas.
It's just air.
Compressed air is literally just the atmosphere of the room that was squeezed, so when it escapes, it just politely expands and rejoins the atmosphere.
It's the only utility that vanishes without a trace.
And because it doesn't cause an immediate catastrophic mess, it totally fails to trigger our evolutionary urgency response. A leak rarely announces itself with a sudden, violent failure, like a gear snapping or a motor seizing.
How does it usually start then?
It usually starts microscopically. Maybe it's a loose thread on a fitting or a rubber hose that slowly dries out and cracks over 6 months of vibration.
Just a slow degradation.
Right. It takes the quiet career path of becoming normal. The human brain is incredibly adept at filtering out constant, unchanging stimuli. It's called sensory habituation.
Sensory habituation,
Yeah.
like when you stop noticing the hum of your refrigerator.
Exactly. If a frequency doesn't change, our auditory cortex just stops registering it as new information. The hiss literally blends into the factory soundscape.
I was reading an editorial on maintenance culture in our sources,
Yeah.
and the author framed this so perfectly. They said, a hiss is not a sound. It is a maintenance request without paperwork.
That is a great way to put it.
Or even better, they said, it's paperwork that learned to whistle. That feels profound to me, because what we're really talking about here isn't a mechanical engineering failure, it's a failure of ownership.
Ownership is the absolute crux of the issue. This is a classic tragedy of the commons on the factory floor. Well, an air leak might be heard by 50 different people over the course of an 8-hour shift, yet it belongs to no one. If a forklift breaks down, the forklift driver owns that problem, right? Their job, cannot proceed until it's fixed.
Right, they have a vested interest in fixing it.
If the conveyor belt snaps, the line manager owns it. But a hiss coming from a random junction box suspended 20 feet up in the rafters, whose job description covers that?
Nobody's. But let me play the role of the stressed out floor manager for a second.
Go for it.
If my production line is still moving, and the pneumatic tools are still getting enough air to drive the screws or lift the heavy parts, who really cares if there's a little ambient hiss in the background?
The as long as it works mentality.
Yeah. The system is ultimately doing its job right.
Mm-hmm.
I have weekly quotas to meet. I have supply chain issues. I do not have the manpower to chase invisible air.
That mindset is the exact rationale that drains hundreds of thousands of dollars from operating budgets. What that floor manager can't see is the hidden operational damage.
Hidden damage.
It's not just a little hiss. When international bodies audit these systems, like under the ISO standards, they find that this lack of maintenance creates a cascading failure across the entire mechanical ecosystem of the facility.
How does a little hole cause a cascading failure?
Well, consider the visual aesthetic of the leak. Imagine a beautifully clean, minimalist design, maybe a brushed aluminum pipe running along a white wall, and right at the joint, there is a tiny pale blue acoustic ripple.
Just a little shimmer in the air where the pressure is escaping. It sounds almost elegant.
Visually, yes, but financially, you have to conceptualize that tiny ripple as a tiny invisible employee.
An invisible employee. I like that analogy.
This employee attends every single shift, 24 hours a day, 7 days a week, holidays included. They produce absolutely zero product. They report to no manager.
And yet they are drawing a massive continuous salary directly from the factory's electricity budget.
Precisely. And they aren't just drawing a salary, they're actively sabotaging the equipment around them.
Okay, I need the actual math on this invisible employee's salary. Let's quantify exactly what this ignorance costs, because I know the dollars scale up incredibly fast from the DOE examples.
Let's walk through the fluid dynamics and the financial math. Imagine you have a single leak, and the hole is roughly 1/4 of an inch wide.
Just a 1/4 inch gap in a fitting. That's pretty small.
And your factory system is running at 100 psi. Fluid dynamics dictate that air at that pressure will hit sonic velocity, literally the speed of sound, as it chokes through that orifice.
The speed of sound through a 1/4 inch hole. Wow.
That single 1/4 inch leak will bleed out over 100 cubic feet of air per minute, constantly.
100 cubic feet every single minute. What does that translate to in hard dollars?
Well, if a plant has just 10 of those 1/4 inch leaks scattered around...
Which, in a massive facility with miles of piping, 10 leaks is basically a rounding error. You could probably find 10 leaks in one production aisle.
Oh, easily. So 10 leaks of that size. To produce the air that is actively escaping through those 10 holes, the compressor requires a specific amount of continuous electrical power. Right. Assuming an electricity cost of just 5 cents per kilowatt hour, which, by the way, is incredibly cheap for industrial power in today's market.
Very conservative estimate.
Very. And assuming the plant operates for 5,000 hours a year, those 10 leaks will cost the facility over $158,000 annually.
$158,000 blown into thin air, literally.
Rejoining the atmosphere at a cost of 6 figures. And the distribution of that waste is really fascinating.
What do you mean?
A typical facility doesn't have uniformly sized leaks. In one documented audit, a plant found 160 leaks of various sizes. They had microscopic ones, maybe 132 of an inch, all the way up to large 1/4 inch blowouts.
Okay, a huge variety.
When they ran the numbers, fixing just the 10 largest leaks, those 1/4 inch ones, accounted for nearly 70% of the total financial savings.
So it's a massive Pareto principle, the 80-20 rule. Or in this case, the 70-10 rule. You don't even have to fix every single microscopic hiss to save your budget. You just have to hunt down the big screamers.
Exactly. Triage is highly effective here. You target the largest orifices first. But let's return to your stressed out floor manager who said, as long as the tools work, I don't care.
Right. My hypothetical manager.
The $158,000 power bill is only the direct electrical cost. The operational ripple effects on the machinery are arguably much worse.
Walk me through how a leak actually damages the physical operation of the plant.
When a system is bleeding 30% of its air volume into the room, the overall pressure inside the piping infrastructure drops.
Okay.
Think of it like having terrible water pressure in your house shower because someone left a garden hose running full blast outside.
Oh, I hate when that happens.
Right. When the pneumatic pressure drops, the tools on the factory floor lose their mechanical force. An air drill designed to spin at 10,000 RPMs might only manage 8,000. The torque on the impact wrenches drops below specification.
So now the assembly workers are taking an extra 2 seconds to tighten every single bolt. The entire line slows down.
Exactly.
And worse, if a bolt isn't torqued to the proper spec because the tool was weak, your product quality suffers. You might have things falling apart in the field.
The secondary costs are massive and hard to even quantify. But the mechanical damage to the compressor itself is the hidden killer.
How does the compressor get damaged?
How does the compressor in the back room react to this pressure drop? It has a pressure sensor. It senses the system is low, so the massive electric motor turns on to pump more air and rebuild the pressure.
Okay, that makes sense.
Because of the leaks, it reaches the target pressure, turns off, and then the leaks immediately drain the pressure away again. So the compressor turns back on.
Oh, I see. It's stuck in a loop. Short cycling.
Short cycling destroys heavy machinery. Large industrial rotary screw compressors are incredibly complex. You have massive metal rotors injecting oil to seal the gaps, heavy bearings, and massive electrical motors.
They aren't meant to just flick on and off like a light switch?
Not at all. The internal electrical switches that turn these motors on are called contactors. These are heavy copper pads that slam together to handle hundreds of amps of current.
Intense.
Most of these systems are only designed to handle 4 to 6 starts per hour. If they start cycling on and off 15 times an hour because they are desperately fighting leaks, the motor overheats.
Wow.
The contactors literally turn into molten slag from the electrical arcing. The lubricating oil breaks down faster from the heat. You are drastically shortening the lifespan of a machine that costs tens or hundreds of thousands of dollars to replace.
Okay, so if I'm that factory manager and my workers are complaining that their tools are sluggish, the assembly line is dragging, and I'm stressed out, my first instinct is absolutely not to go walking around with a notebook looking for invisible hisses.
What is your instinct?
My first instinct is to march back to the compressor room, look at the master dial, and just crank up the pressure.
The classic fix.
Right. If the tools need 100 psi to run, and the leaks are dragging us down to 85, I'll just set the compressor to 120 psi to forcefully overcome the leaks and get my tools working again. Problem solved, right? Let the compressor work a little harder.
That is the single most destructive action you can take. And tragically, it is the most common knee-jerk response in the entire industry.
Really? Why is it so bad?
It creates a thermodynamic nightmare known as artificial demand.
Artificial demand. Let's dig into the physics of that. Why is cranking the dial such a disaster?
There is a golden rule in compressed air thermodynamics. For every 2 psi you increase the discharge pressure at the compressor, you require 1% more electrical energy from the motor.
Okay, so if I crank my pressure up by 20 psi just to compensate for the sluggish tools, I just permanently added 10% to my already astronomical power bill.
At a bare minimum.
Yeah.
But the real tragedy of artificial demand is what happens out on the factory floor. You cranked up the pressure to feed the tools, right? But what else is connected to that exact same network of pipes?
The leaks.
The leaks. When you increase the systemic pressure, you aren't just pushing more air to the tools, you are pushing air harder against the leaks.
Oh, no.
Bernoulli's principle and orifice flow equations dictate that the higher the pressure behind a hole, the faster and more voluminous the fluid escapes through it.
So you just spent 10% more on electricity to forcefully blow even more air out of the exact same holes you were trying to ignore.
Exactly. You made your $158,000 loss significantly worse. You increased the wear on the compressor, and the tools might still be starved for air because the leaks are now consuming a much larger share of the total volume.
That is brutal. It's like trying to fill a bucket with a hole in the bottom by turning the garden hose on blast. You're just making a much bigger mess much faster, and the bucket still isn't full.
It's a losing battle against physics.
Yeah.
So we've established the crime scene, the thermodynamic inefficiency, and the devastating financial cost. The obvious question becomes, how do we break the psychology of normalization?
Right. How do we take an invisible, ownerless problem and give it a visible owner?
Which brings us to the core framework of how to actually fix this. It's a very specific 6-step behavioral shift that fundamentally changes how a factory handles this utility.
And based on the sources, we're calling this the Audible Loss Method.
Yes, the Audible Loss Method. The brilliance of this method is that it treats the issue as a cultural problem first and an engineering problem second.
That's a great distinction.
You cannot just buy a shinier, more expensive compressor to solve this. You have to change how human beings interact with their physical space.
Okay, so let's go through the steps. Step 1 of the method is detect. Now, we already talked about sensory habituation and how loud a factory is. You can't just rely on a guy with a clipboard cupping his hand to his ear while massive stamping presses are slamming next to him.
Human ears are entirely inadequate for this in an industrial environment. The standard technological solution is the ultrasonic acoustic detector.
Ultrasonic, so above human hearing.
Exactly. When pressurized air escapes through a tiny jagged crevice, it creates a turbulent flow. That turbulence generates high-frequency sound waves, ultrasound.
Okay.
We can't hear them because they exist above the threshold of human hearing, and they are drowned out by the lower frequency clatter of the factory machines. But an ultrasonic detector hears them perfectly.
Wait, if the factory is deafeningly loud, how does a microphone isolate a hiss? Does it just block out the noise?
It uses a technology called heterodyning.
Heterodyning.
Yeah, it's not a regular microphone. It's specifically tuned to only pick up frequencies in the 5 to 45 kilohertz range, which is well above the rumble of a motor or a forklift. The device captures that ultrasonic signal and translates it down into a lower audible frequency that a human can hear through a pair of heavy, noise-canceling headphones, or it displays it as a visual decibel graph on a screen.
So you can literally point this device around a loud factory, scanning the raptors like you have a radar gun, and it will pinpoint a tiny hiss from 20 feet away through all the noise.
It makes the invisible highly visible. It's basically magic. And if you are in a smaller shop and don't have a few $1,000s for an ultrasonic detector, the old-school fluid dynamics test never fails. Soapy water. You spray a mixture of soap and water on a suspected joint. If it bubbles up, you have a leak. It's tedious, but it is foolproof.
Which leads directly into step 2.
Yeah.
Tag. And from everything I've seen in the manuals, this is the most crucial cultural shift in the whole method.
It absolutely is.
You don't just find the leak, write it down on a piece of paper and walk away.
I'll put it in a spreadsheet later, is the graveyard of leak management. The heroic spreadsheet managed by one well-meaning engineer on a Tuesday afternoon does absolutely nothing to change the culture on the floor.
Because the leak remains invisible to the people actually working next to it.
Right.
Step 2 requires a physical intervention, a 2-part physical tag. When you find a leak with your ultrasonic detector, you take a brightly colored tag, usually neon yellow or neon red, and you physically zip tie it directly to the leaking pipe, valve, or hose, right there, at the exact coordinates of the failure.
The psychology of the visual marker is profound. You are taking the invisible hiss, the thing everyone habituated to, and you are giving it a physical neon body.
It's like a scarlet letter for a broken pipe.
Exactly. You are forcing every operator, every manager, and every maintenance worker who walks by to physically look at their own waste. It breaks the habituation.
That's powerful.
And because it's a 2-part tag, there is a physical workflow. You tear off the bottom stub of the tag. The main body of the tag stays on the pipe, signaling to the floor, yes, management knows this is leaking. And you put the stub in your pocket.
Which triggers step 3, track. Okay, so I've hung a neon tag on a pipe. How does a piece of cardboard actually force a busy mechanic to fix it instead of just walking past it again?
The stub of the tag is the bridge between identification and action. You take that stub to the maintenance planner. It contains the exact location, the estimated size of the leak based on the decibel reading, and the date it was found.
Oh, so it has all the metadata.
Yes. That stub is used to generate a formal, logged maintenance work order in the facility's software system. This is how you solve the ownership problem. The leak is no longer just factory noise. It is a logged task assigned to a specific maintenance technician with a deadline. It has an owner.
A hiss is a task waiting for an owner.
Yeah.
I love that.
Okay, so step 4 is repair. But let me ask a practical mechanical question here. When we say repair a leak, what are we actually doing? Are we just wrapping duct tape around a rusty pipe or replacing a straight 20-foot section of steel piping because a hole rusted through it?
It is remarkably rare for a straight run of steel or aluminum pipe to spontaneously spring a leak. I mean, unless the facility has completely failed to manage internal moisture and corroded the pipe from the inside out.
Right.
The vast majority of leaks occur at the transition.
Joints and the connections.
The weak points of any fluid system, the threaded couplings, the flexible rubber hoses that dry out, lose their elasticity, and crack due to constant vibration and thermal cycling.
That makes sense. The quick disconnect fittings, the brass chucks where a worker physically plugs and unplugs an air tool 100 times a shift. The internal O-rings in those fittings degrade very quickly, and specifically the FRLs. The filter, regulator, and lubricator assemblies that sit right before the tool.
There was another specific component that came up repeatedly in the leak audits in our sources. Condensate traps. What are those, and why do they leak so much?
The condensate traps. Remember how squeezing the air squeezes all the water vapor out of it? It's like squeezing a wet sponge.
Yeah.
That water condenses inside the pipes and naturally flows downhill to the low points in the system. If you don't get that water out, it destroys the tools. So engineers install condensate traps or drains at the bottom of the pipes to periodically spit the liquid water out.
Sounds like good engineering.
It is, but this is where human laziness ruins good engineering.
What do people do to them?
Well, automatic traps are great, but they get clogged with rust, scale, and compressor oil. They require routine cleaning. So a maintenance worker gets frustrated with constantly cleaning the clogged automatic trap. They remove it entirely and they replace it with a simple manual ball valve.
It's a basic liver.
Exactly. But they certainly don't have time to walk around the massive factory opening and closing 50 manual valves all day to let the water out. So what is the path of least resistance?
Oh no, they just leave it open?
They just crack the manual valve open a tiny sliver, and they leave it there permanently.
So it's constantly blowing a mixture of air and water out onto the floor.
It is a designed, intentional leak, created purely out of convenience. And the math on this is horrifying. A single manual drain left cracked open might waste 5 cubic feet per minute continuously, 8,760 hours a year.
Wow.
That one single valve, left open because someone didn't want to clean a trap, costs the facility over $425 a year in wasted electricity. And a large plant might have dozens of them.
So repairing leaks isn't just about replacing broken O-rings. It's about correcting lazy engineering and bad habits.
Yeah.
Okay, step 5 is verify. Why is this a separate step? If the mechanic fixed it, isn't it done?
Trust, but verify. Fluid systems are tricky. You have to close the loop. The technician goes out, replaces the brass fitting, and cuts the neon tag off.
Right.
But you need the supervisor or the leak auditor to go back during the next cycle with the ultrasonic detector and verify that the repair actually worked. Often, taking a wrench to a threaded pipe to tighten one joint just shifts the mechanical stress and causes a new leak 2 inches down the line.
Oh, I've done that in plumbing. Fix one leak, create another.
Exactly. You have to verify the acoustic signature is completely gone.
And finally, step 6, involve. This feels like the glue that holds the whole method together.
This is where you cement the new culture. You have to train the machine operators, the people actually standing next to the pipes 8 hours a day, to recognize and report the leaks themselves.
Give them ownership.
You give them the authority and the supply of neon tags. If a line operator feels empowered to tag a leak on Monday, and they see the maintenance team actually show up and fix it on Tuesday, a massive psychological shift occurs.
They realize the company actively cares about eliminating waste.
Exactly. The leak stops being background scenery and becomes an actionable defect.
Okay, so let's say I'm that stressed out factory manager. I have seen the light, I bought the ultrasonic detector, I bought 1,000 neon tags, and I deployed the Audible Loss Method. My team hunts down 100 leaks, we fix the 20 biggest ones, we close all the cracked manual valves, and we suddenly stop bleeding 30% of our air.
Congratulations.
I'm a hero, my tools have pressure again. Can I go take a nap now? Is the job done?
The job has just begun. If we expand our view to the holistic optimization of the entire system, fixing the leaks is only phase 1. In fact, there is a cruel irony in pneumatic engineering.
What's that?
If you fix all your leaks, but you leave your compressor running the exact same way it was running before, you actually will not capture the financial savings you just created.
Wait, hold on. Why not? If I am leaking 30% less air into the room, the compressor doesn't have to work as hard. Shouldn't my electrical meter slow down and my power bill automatically drop?
It depends entirely on the mechanical control system of your compressor. And this requires us to look beyond the leak itself and look at the machine in the back room.
Okay.
But before we diagnose the compressor, let's look at a brilliant, highly practical diagnostic tool from the DOE manuals. If a plant manager wants to know their overall leak load, but they haven't installed expensive digital flow meters on their pipes, how do they figure out how much air they are losing?
The start-stop drawdown test. I was reading about this procedure, and it is so elegant. It sounds like something a clever mechanic would invent in their garage, but it perfectly scales up to massive industrial complexes.
It relies on basic volume and pressure math. It's beautifully simple. You execute this test during a non-production hour, say Sunday morning at 2 a.m. when the plant is completely shut down.
So there's no legitimate demand for air. None of the robotic arms are moving. No one is using a pneumatic wrench.
But the leaks are still leaking.
Exactly. The holes in the pipe don't care what day it is.
Yeah.
So you go to the compressor room, you turn the compressor on, and you let it pump the entire piping system up to its maximum operating pressure, let's say 100 psi.
Right.
Once it hits 100, you hit the emergency stop. You turn the compressor completely off. Now you stand there with a stopwatch, and you watch the main pressure gauge. You time exactly how long it takes for the system pressure to drop by 20 psi from 100 down to 80.
Because the entire system is sealed, the only physical way air is leaving the pipes and causing the pressure to drop is through the leaks.
Correct. So you log your drop time, then you turn the compressor back on, and you use your stopwatch to measure exactly how long it takes the motor to pump the system back up from 80 psi to 100 psi. That is your rise time.
Okay, I have my drop time and my rise time. How does that give me a percentage?
The math is just a ratio of the work done. You take the rise time and you divide it by the total time of the cycle, which is the rise time plus the drop time. That ratio gives you your exact systemic leak percentage.
Give me an example.
For example, if it takes the compressor 2 minutes to pump the system up, and it takes 3 minutes for the leaks to drain it back down, your total cycle time is 5 minutes. 2 divided by 5 is 0.4. Your system is leaking 40% of its total capacity.
Boom. No expensive consultants, no ultrasonic meters required just to find out how bad the bleeding is.
It's so smart. So once you know that percentage and you deploy the tags and fix the leaks, we get back to my earlier question about the compressor controls. Why wouldn't my power bill go down automatically after I fix a 40% leak load?
Because of how older fixed-speed compressors mechanically regulate themselves. Many legacy systems use what's called modulating control.
Modulating control.
Basically, the massive electric motor is designed to spin at full speed all the time, 100% of the time. When the factory doesn't need air, say, during a shift change or after you've fixed all your leaks, a mechanical butterfly valve on the air intake just closes up.
It just blocks the air.
It physically chokes off the air supply so the compressor stops pumping air into the pipes.
But the heavy electric motor is still spinning at full speed.
Yes. And the aerodynamics of that are terrible. Imagine driving your car on the highway, keeping your foot mashed on the gas pedal, but using the emergency brake to control your speed.
That sounds like a great way to destroy a car.
It is. Even when a modulating compressor is completely choked and pumping 0 cubic feet of air, the internal mechanical friction and the aerodynamic drag of spinning those heavy metal rotors in a vacuum means it is still consuming about 70% of its full load electrical power.
Oh, wow. So if I fix my leaks, the compressor just closes its throat valve a bit more because it doesn't need to pump as much air, but the electrical meter on the wall is still spinning almost as fast as it was before.
You saved the air, but you failed to save the power. To actually capture the financial savings of the Audible Loss Method, you have to upgrade your compressor controls, or better yet, introduce a VSD compressor to your fleet.
Variable speed drive.
Right. A VSD compressor has a highly advanced electronic inverter drive that actively changes the frequency of the electricity going to the motor. It actually slows the physical rotation of the motor down to perfectly match the exact real-time demand for air in the plant.
So it adapts.
If the plant only needs 50% capacity, the motor dynamically slows down and spins at 50% speed. And the physics of variable frequency drives mean it uses roughly 50% of the electrical power.
That makes infinite sense. But let me push back on this. If VSDs are so perfect and solve all this wasted energy, why hasn't every factory on Earth already installed one? What is the catch?
Capital cost and electrical sensitivity. VSD compressors are significantly more expensive upfront than fixed-speed machines. Furthermore, the electronic drives can introduce electrical harmonics back into the factory's power grid, which can mess with highly sensitive robotic equipment if not properly filtered.
So there's an engineering trade-off.
But the return on investment is undeniable. The modern best practice in a large facility with multiple compressors is to use a hybrid approach.
How did that work?
You have your older fixed-speed compressors handle the base load. They turn on and run at 100% capacity, which is their most efficient state, to handle the bulk of the factory's constant work. And then you install one single VSD compressor to act as the trim compressor.
Just trim compressor.
It ramps its speed up and down to elegantly handle the fluctuating peaks and valleys of demand on top of the base load.
So the VSC is basically riding the waves, keeping everything perfectly balanced without wasting power. Okay, so we've fixed the leaks, we've tuned the compressor controls. But we also have to look at the physical plumbing, the distribution system itself.
The pipes are the arteries of the factory. Think back to the pressure drops we discussed earlier. Air friction inside a pipe is a relentless energy thief.
Right.
If you try to force a massive volume of air through a pipe that is too small, the air molecules violently scrape against the pipe walls. That friction creates resistance, which causes the pressure to drop by the time it reaches the end of the line.
Which tempts the floor manager to crank up the master pressure, which creates artificial demand, which makes the remaining leaks blow harder. It is all terrifyingly connected.
It is a closed-loop system of failure. So how do you defeat pipe friction? Engineering provides two highly effective solutions. First, you loop the piping.
Like building a literal circle of pipe around the factory ceiling.
Precisely. In older factories, you often see a single, straight header pipe running down the center of the building, dead-ending at the far wall. If 50 guys are working on that line, all the air has to travel down that single path, fighting friction the whole way.
And losing pressure.
But if you simply take a pipe and connect the dead end back to the compressor room, forming a closed loop, the physics change dramatically.
Because the air can go both ways.
Yes, parallel fluid dynamics. Air can now travel in two different directions around the loop to reach any specific tool on the line. Fluids always seek the path of least resistance.
That's brilliant.
By halving the distance the air has to travel and splitting the volume, a single looped system can reduce pressure drops by 75% compared to a straight dead-end pipe.
That is an incredible return on investment for just connecting two ends of a pipe together. What is the second way to defeat friction?
Pipe diameter. And the mathematical physics here are incredibly generous. The Hagen-Poiseuille equation, which governs fluid flow, shows us that pressure drop is inversely proportional to the radius of the pipe to the fourth power.
To the fourth power.
In practical terms.
Right.
If you double the diameter of a pipe, say going from a standard 2-inch pipe to a 4-inch pipe, you don't just cut the pressure drop in half, you cut the pressure drop by roughly 75%.
Wow. Why is it such a massive jump?
Surface area to volume ratio. The friction only happens at the boundary layer, where the air touches the physical metal wall of the pipe. When you double the diameter, you massively increase the internal volume of the pipe without proportionally increasing the wall surface area.
So most of the air isn't touching the walls.
The vast majority of the air flows smoothly through the center of the pipe, entirely untouched by wall friction.
So when a factory is expanding and they build a new wing and the contractor just taps a tiny 1-inch line off the main header and runs it 300 feet to power a new machine, they're essentially suffocating that machine with friction.
And forcing the main compressor to work much harder to push the air through that tiny straw. The engineering mantra is, always oversize your piping. The cost of a slightly larger diameter pipe is negligible compared to the energy savings it generates over a 20-year lifespan.
Let's pivot to air quality, because we established that the air has to be bone dry and clean, right? We mentioned the air dryers and filters in the beginning of the journey.
Yes. Air emerging from a compressor block is incredibly hot and 100% saturated with water vapor. If you don't condition it, it will literally rain liquid water inside your pneumatic tools, washing away their internal lubrication and resting them solid.
Yeah, rain in the pipes is bad.
So you must dry the air. But here is the massive operational trap: overdrying.
How can air possibly be too dry? I would think bone dry is the goal.
It's not that the air is too dry for the tools to function. It's that the physical process of drying air is exponentially expensive the drier you get. Most factories use refrigerated dryer.
Okay.
They act like an air conditioner, cooling the compressed air down to about 2 degrees Celsius or 35 degrees Fahrenheit. The water condenses, drops out, and the air is dry enough for 90% of indoor industrial applications. But sometimes a facility manager thinks, hey, dryer's better, let's buy the premium option, and they install a desiccant regenerative dryer.
What does a desiccant dryer do differently?
Instead of refrigeration, it forces the air through massive twin towers filled with chemical desiccant beads, like those little silica gel packets you find in a shoebox, but on an industrial scale.
Oh, wow.
These beads strip the moisture out chemically, bringing the dew point of the air down to minus 40 degrees.
Minus 40. When would you ever need it that dry?
It is absolutely necessary if your air pipes run outside between buildings in a freezing Canadian winter because you can't have ice forming in the lines, or if you are painting cars and need surgically clean air.
But otherwise.
But here is the penalty. The chemical beads quickly saturate with water. To dry the beads out so they can be used again, the dryer requires taking up to 15% of your newly compressed, highly expensive air and blowing it backward through the offline tower to purge the moisture.
Wait, You are intentionally throwing away 15% of your total air production just to run the dryer.
Yes, it's called purge air. The rule of thumb in the industry is drying air to a -40-degree dew point costs 5 to 10 times more in energy than drying it to a +2-degree dew point.
Yeah.
If your factory floor doesn't absolutely require surgically dry air, you are literally burning money. Do not overdry your air.
And what about the filters?
Filters are necessary to remove ambient dust and the aerosolized lubricating oil that escapes from the compressor block, but as they capture dirt over months of operation, the microscopic pores clog up. A clogged filter acts exactly like a restrictor plate on a race car. It causes a massive pressure drop. If you have a 100-horsepower compressor and you neglect your maintenance so badly that the clogged filters cause a 10 psi pressure drop across the housing, you are spending over $1,600 a year in wasted electricity just to forcefully shove the air through the dirt.
Change your filters. It's exactly like your home HVAC system, but 1,000 times more expensive. Now, I want to talk about my absolute favorite part of this whole ecosystem.
The human element.
Yes, the inappropriate uses of compressed air. Because when you put a hose shooting high-pressure invisible power into the hands of a bored or clever human being, they will find a way to abuse it.
The creativity on a factory floor is boundless and deeply expensive.
I was looking at audits of how people actually use these hoses on the floor, and it is absolute comedy. Some of these are crimes against thermodynamics, using a 100 psi air hose to casually sweep sawdust or metal shavings across the floor.
Using $10 an hour of heavy industrial electrical power to do a job that a $20 push broom could do perfectly well.
Or, my absolute favorite, using expensive compressed air for personal cooling. Some guy on the line just aiming the pneumatic hose down the back of his shirt because the factory floor is hot in July.
It is definitively the most expensive desk fan in the history of the world, and it is actually incredibly dangerous.
How so?
People don't respect the kinetic energy of a 100 psi jet of air. If you accidentally dead-end a high-pressure nozzle against your skin, it can forcefully inject an air bubble directly into your bloodstream through the pores.
Oh my God.
That is an air embolism, and it can travel to your heart or brain and be fatal. But strictly from an energy perspective, using a pneumatic hose for open blowing, personal cooling, or drying off freshly washed parts is a disaster. You're just venting money. Factories should install low-pressure electric blowers, squirrel cage fans, or physical brushes for those tasks. Keep the high-pressure compressed air strictly for the pneumatic tools that actually require massive torque.
Okay, one last piece of system optimization. We talked way back at the beginning about how 80% of the electrical energy put into the compressor is instantly lost as the heat of compression. What happens to that heat? Do they just vent it outside like an exhaust pipe?
Traditionally, yes, it's just treated as waste. But highly efficient modern smart factories don't vent it. They use heat recovery.
Heat recovery.
If you have an air-cooled rotary screw compressor, it is functionally operating as a massive industrial space heater. All you have to do is attach some simple sheet metal ductwork to the compressor's cooling exhaust fan. In the winter months, you route that ductwork to blow that hot air directly onto the factory floor to heat the building. In the summer, you flip a mechanical damper and vent it outside.
You're directly offsetting your natural gas or HVAC heating bill by capturing the waste heat from the compressor motor.
Yes. Thermodynamics allows you to recover 50 to 90% of that thermal energy. You can even use liquid heat exchangers to capture the heat from the compressor oil and use it to heat up water for industrial parts washing processes or to preheat water going into the facility's boiler.
That's incredible.
When you combine heat recovery with fixing your leaks, you completely change the economic and carbon footprint of that machine.
So let's bring this all together. If I do all of this, if I embrace the cultural shift of the Audible Loss Method, I buy the ultrasonic detectors, I hunt down the big leaks, I tag them with neon zip ties, I track them through the maintenance system, I get my team to fix the FRLs and replace the cracked manual valves.
That's a lot of work.
It is. I stop my guys from using the air hose as a personal air conditioner. I buy a VSD compressor to gracefully trim the load. I loop my pipes to kill friction. I stop over-drying my air, and I recover the exhaust heat. What is the realistic end game here? Can I actually get my factory's leak rate to 0%?
0% is a mathematical impossibility in a dynamic, vibrating industrial system with thousands of moving parts, flexible rubber hoses, and human operators. Entropy guarantees there will always be a leak.
Right.
But engineering standards suggest that reducing your leak load to between 5 and 10% of your total system volume is a highly achievable, cost-effective target for a rigorously maintained facility.
That's a huge improvement from 30%.
Going from a 30% waste load down to a 5% waste load transforms your facility's profitability. It reduces the mechanical wear and tear on your compressors, it stabilizes the pressure for your pneumatic tools, it speeds up your assembly line, and it dramatically lowers your corporate carbon footprint.
It is an incredible journey. We started with this little hiss, this tiny pale blue acoustic ripple that everyone on the floor was just walking past and ignoring.
Just a part of the soundscape.
And we unpacked it to reveal thermodynamics, six-figure electrical costs, the dangers of artificial demand, and massive systemic mechanical failure. But more importantly, we found the behavioral solution. Compressed air is a luxury utility. It is a high-performance kinetic power delivery system that demands respect, not an endless free breeze. And the Audible Loss Method detect, tag, track, repair, verify, involve isn't just a laminated maintenance checklist.
No, it's a culture shift.
It is a fundamental ethical engineering shift. It is about taking something invisible and ownerless and forcefully assigning it visibility and accountability.
It is about refusing to let profound waste become normal.
And I think that brings us to a really fascinating, deeper place to wrap this up. Because the underlying philosophy we've been discussing today applies to so much more than just pneumatic pipes and air compressors.
It absolutely does. We have spent this entire time dissecting literal whistling air leaks in a manufacturing plant. But the core underlying issue here is the immense danger of normalization.
Normalization of deviance.
Sociologists call it exactly that. When a loss or a failure doesn't cause immediate catastrophic damage, when it doesn't leave a massive puddle on the floor or shut down the company's servers or set off an alarm, human beings have this incredible and highly dangerous capacity to adapt to it. We habituate.
It becomes background noise.
We accept the unacceptable simply because it was there yesterday. So as you go back to your desk or your team or your life today, I want you to ask yourself, what are the metaphorical compressed air leaks in your organization?
Wow.
What inefficient workflow, what redundant weekly meeting, or what broken communication process has been going on for so long that everyone just walks right past it without turning their head?
That is something to think about. Remember, a hiss is just a task waiting for an owner. What hiss do you need to tag today?